So in this arrangement, you can kind of figure out what's happening here, right? Is it kind of obvious? I start the ball at the top of the ramp, I let it go, and it rolls down the ramp, hits the spring, stops. Does that make sense? No. I'm picking snapshots. It's as if I set this whole thing up and I have a camera that can take 4 pictures. I took 4 pictures of it as it went. The object never stays here, right? The spring will shoot the ball back out and it'll go back up the ramp, probably stop here, turn around and go back. And if nothing takes energy out of this system, it will do this forever. Does that make sense? Do you follow along? It's a simple idea here. A real system wouldn't do that. There would be air resistance and friction, and eventually the system would stop moving, settling in the area where there's the lowest amount of energy, probably somewhere around here. But in an ideal system, this could go on for a long time. Now, there are things about this system that scream conservation of energy. And if you don't know what they are, if you're having trouble and you're struggling, first, this problem is about a single object. That's incredibly important. Single object problems can use the rules of conservation of energy because we're applying the energy to one object in the system. Now, I'm not saying that the rules don't apply to multi-object systems. What I am saying is that if you want to use conservation of energy, the whole gravitational potential, kinetic, and elastic potential energy, we're only going to apply them to one object at a time and follow the energy through that object. So you look for things like a change in height. That's a clear and excellent way to begin a problem, saying, wow, a change in height probably tells me gravitational potential is going to exist for the object here. I'm going to establish a reference level, make that reference level my 0, and there's no gravitational potential here. You know, that's what you're looking for. Anytime an object interacts with a spring, that's probably a conservation of energy question. Look for where that spring is. Likely the energy is going to be moving from kinetic to elastic potential in the spring. And we've seen combinations of all 3 where the object has interactions with all 3. Where that ends is in situations where it's not clear where the energy goes. And the most common situation, one object interacts with another object. Now, in physics, interacting with another object may sound like an infinite number of possibilities. Interacting with another object means colliding. It sounds complicated, but it's not. Interacting, we interact through gravity, but that requires an entire planet. For everything else, interaction requires a force. And for that, it requires contact. So in most cases, an interaction means a collision. One object hits another object. Now, before that collision, the first object, let's say that one of them is stationary and the other one is moving. Before that collision occurs, the first object has kinetic energy. It's moving. Can't be a collision without one of the objects moving, right? What happens during the collision, though, is not clear and can't necessarily be predicted. After the collision, there are a number of possible outcomes. And all of them depend on some factors that are tangible, meaning easy to see, and some factors that are intangible, meaning more difficult to see. It is possible that the first box will stop and the second box will keep going. That's a possible outcome. It's possible that both boxes might keep moving. Maybe they both have a little bit of velocity in this direction. Who knows? Maybe the first box bounces off of the second box and this box keeps going. And there's a large possible number of outcomes. The thing I want you to start understanding about a collision is that the outcomes depend upon how the energy is divided up amongst the objects. The outcome mostly depends, on how the energy is divided up amongst the objects. The problem, I'm trying to talk really slow so I don't have to repeat myself, how the energy is divided up amongst the objects. The problem, and this is hard, is that in a collision, the energy might not be conserved. Most importantly, it is very unlikely the kinetic energy will be conserved. In a collision, it is very unlikely that the kinetic energy will be conserved. Collisions make noise. Collisions create heat. Collisions cause dents. Collisions change the shape of objects. And so it's very unlikely kinetic energy will be conserved. The energy is going to be transformed into other forms that may not easily be able to be seen. They're intangible. So when one object collides with another, you're probably not going to be able to rely on energy as a means of your solution. Now, I want to be crystal clear. A collision is the instant before contact and the instant after contact. What I've drawn here isn't the collision because there's still a lot of time before that first object hits the second. A collision is the instant before contact and the instant after. When we deal with collisions, we're dealing with an incredibly short amount of time. In almost all circumstances, we are dealing with the moment before they touch and the moment after they separate. And we're not worried about the collision itself, and we're not worried about anything that happens way after or anything that happens way before. The collision is just in that moment. And here's the crux. Collisions don't conserve energy for the most part. There's only a certain class of collisions that do, and I'll talk about that way later. Collisions do conserve something else. There's another principal quantity we haven't discussed. That principal quantity is momentum. Now, momentum is a loaded term because you've heard the phrase momentum before. It's used often in public media. It's used in lots of conversations in many different disciplines. And in most cases, momentum has the same definition. It's just that it's usually been slanted a little bit towards whatever it is you're talking about. We talk about institutional momentum. How many of you have heard a phrase like that? Institutional momentum. It's hard to get a group of people to change their behavior because the behavior is often based in the institution. We teach schools in classrooms that have 45-minute periods, and we put 30 kids in a classroom, and I talk to you about physics. It's hard to change that. There's probably better ways to do it, maybe even more interesting ways to do it with better success. But schools have institutional momentum. We've been doing it this way for a long time. We know how to do it this way. We don't want to change. Momentum is like that. Momentum is inertia for objects that are moving. That's what momentum is. It's another way of measuring inertia. It is the inertia for objects that are moving. So I don't want to do this, but I want to make sure we get all the things down. The word inertia, if you'll remember, has kind of other meanings. Resistance to change. So objects with momentum want to resist changes in their motion. I hate to use this metaphor, but I've been using it for 26 years. It's just harder to use it now. But a bullet doesn't weigh very much. Anyone of you can pick it up, it's just a couple of grams. It's dangerous because it has a lot of momentum when fired. It's not hard to change when it's just sitting on your desk, right? It weighs about a handful of paper clips weigh about the same. But you give it 300 meters per second of velocity, it is suddenly far more difficult to change its motion. So momentum is based on velocity, but it's based on mass in equal measure. Momentum is mass times velocity. I know you're saying, well, that's just like kinetic energy. No, it's not. Momentum is a different quantity. First, the velocity isn't squared. I know that seems like no big deal. It's a big deal because momentum is a vector. It takes the direction from the velocity. So momentum has direction. Energy doesn't. Energy never had direction. Momentum has direction. And because of that, it is expressly different. The bad thing, the symbol for momentum is a lowercase p. I know. It doesn't make sense. But they couldn't use M. So they went to the next letter, I guess, that they thought they could use. They could use a smiley face for all I care, but the symbol we're using is a lowercase p. Also, this part sucks, it has no unit that has a special name. So kilograms, meters per second is the unit of momentum. No special name. I'm going to be careful here because remember, that's different. Kilograms, meters per second squared, Newton, force. Kilogram, meter squared per second squared, joule, something else. But kilogram meter per second has no special name and is the unit we use for momentum. Now, here's why I have to teach you about momentum. All collisions conserve momentum, 100%. That's what's important. All collisions conserve momentum. All of them. No exceptions. I don't have to say anything else. All collisions conserve momentum. In every case, under all circumstances, no matter what, there's no exceptions, no ifs, no only if, no for this instance, all collisions conserve momentum. Which means if you add up the momentum of the objects before, it has to equal the momentum of the objects afterwards. It's that straightforward. And the reason I need you to know it is because every single FRQ has a collision in the middle of it, and then does something about energy, or then does something about force, or then does something about motion equations. They have collisions everywhere. But the collision part of the problem is only the instant before they touch and the instant after they touch. So, for just a couple of quick examples so I can show you the variety of problems. And when I say variety, there are three different kinds of problems. Okay, 3, and that's it. So the first kind of problem is the most likely problem you will see on the exam for collisions. And although we will study this in a little more depth second semester, for right now, I want to describe for you the most likely scenario. So 5 kilogram box, 10 kilogram box, and 5 meters per second. These collide, and when they do, the two boxes stick together. They stick together and move off with one velocity. So they become one box with a mass of 5 plus 15 kilograms. I'm sorry, 5 plus 10 kilograms. All right. This has a name. It's called a perfectly inelastic collision. A lot of words there. Unlikely to come up on the exam, but if they say they collide in a perfectly inelastic collision, they're saying they stick together. That's what the statement means. Perfectly inelastic. It's the stupidest phrasing ever because inelastic collisions by definition don't conserve energy, so it's saying it perfectly doesn't conserve energy. It's a stupid statement. And so physicists, not good at English apparently, but this is what they've decided to do. Because this is really the most imperfect collision because they lose the most amount of energy. But that's not up to me. I didn't get to make the names. Super stupid, easy to do. Okay, this is a super simple problem. First, remember, momentum has direction. So before you're asked to do a problem, just pick a direction, call it positive. Draw a big arrow at the top. The collision is taking place here in the middle. We're looking at the instant before and the instant after, but pick a direction, call it positive. Afterwards, list out the things with momentum on the left, set them equal to the things with the momentum on the right. So let me do this different. mv for the box that's moving plus mv for the box that's stationary equals m plus m times v. These objects have the same velocity. Join them together, give them one value for v. Perfectly inelastic collision. So 5 times 5 is positive, plus 10 times 0 equals 5 plus 15 times how fast are they moving together? Well, that's what we'll figure out. This is a collision. All collisions like this. Left side, 25. Right side, 20V. Yeah, I did it again, didn't I? Sorry, expect more from us. We teachers are lame. So 25 equals 15V. So V equals 5/3 meters per second. It's positive, so they keep moving to the right. All right? Not challenging, I don't think, but not terrible. Hello. All righty. Move on to the next type. Now, the next type has ambiguity. And you'll understand why when we start. You'll notice that even in this one, I'm not going to change the beginning at all, although I could. I don't want to try and create confusion that doesn't need to be there. All right, in this collision, the boxes don't stick together. In this collision, they stay separated. Back to this collision. If they don't tell me anything special about it, it's just what we call an inelastic collision. So we didn't say it was perfectly inelastic, but inelastic is an entire category of collisions. Most collisions are inelastic. And all that means is it doesn't conserve kinetic energy. That's what inelastic means. Doesn't conserve kinetic energy. That's all it means. Now, I don't know the answer to this collision. Look at it. There's no way to know the answer. In this collision, the possible answers are almost infinite. Because I have my momentum before, which is still 25. But afterwards, it's 5 times V5 plus 10 times V10. That's a lot of possibilities, right? In a collision, if the two objects don't stick together, then there's a lot of possible answers. In collision questions, they've got to give you enough information so that you can use the collision to do something. So if you have a collision where one object strikes another, they would have to tell you something about the answer in order for you to figure out the other portion. In a collision, the velocities of these two objects can be distributed in a lot of different ways. It really just depends on what happens when they strike each other. There are instances, perhaps, where more of the energy will go to one box than the other. If one of them is much harder and has a more rigid surface, and the other one is softer, well, then under those circumstances, more of the energy might go to one than the other. And there's no way to predict that or figure that out. There's no physics that tells us that. So in a problem like this, they're going to have to give you either one of these velocities, or they're going to have to give you some information about what happens later. Like, either they say this one has 1 meter per second after the collision, or, and this is how they'll indirectly do it. They'll put the whole thing on a table, and they'll say the 10 kilogram box landed over here. How fast was the 5 kilogram box going? They're expecting that you know the rules regarding a projectile will lead you to the velocity that it left the table, and can then work backwards to figure out what that velocity must be. That's the kind of stuff they do on the exam. Now, in the unit we're studying, probably not that one. In the unit we're studying, probably more like this. Box number 2 was connected to a string. And after the collision, box number 2 swung upwards to here. How fast was box number 1 going after the collision? We've done this problem, right? We've done a problem where we talked about the change in kinetic energy going to potential energy for something that swings upwards. We did the reverse, swung downwards, but same idea. So we would use that to figure out how fast it was going, and then use this to figure out this one's speed after the collision. That's the kind of stuff they're going to put on the exam. But in this collision, in a standard inelastic collision, the expected outcome isn't known unless you have more information about what happened during the collision. Okay so far? I know it's a lot, but collisions are actually usually very straightforward. There was something before and it's something after. You have to ignore all the stuff that happens way after and focus the collision on just the moment before and the moment after. Most collisions in this class end up being perfectly inelastic. In almost all cases, when I pull up the exams, they almost always stick together in the course of the collision. That is the most common type of collision they do, because they don't have to worry about this problem of not having enough information. However, I hate to say it, there's one more. Less than 1% chance of this being on the exam. Okay, less than 5% chance of this being on the exam. In all the years I've been teaching AP Physics C, there's been one collision like I'm about to describe on the exam, and only one. And it was worth 4 points on one FRQ. You could earn 3 of those 4 points without finishing the problem. However, you need to be prepared for it. It has a special name and all that kind of stuff. So let's start here. Let's do it all again. 5, 10 kilograms. Collision occurs here in the middle. And when we're done, we've got 2 boxes. Two velocities. They don't stick together. But this one has a name. They have to say it for it to be the problem. I mean, they have to tell you this happened. It's called an elastic collision. Again, no way to know that it's an elastic collision unless they tell you. But elastic collisions are special. And they don't really happen in nature. The conditions to have an elastic collision in nature are extreme. They happen at the subatomic level. And you can kind of get them in the real world, but really not. No collision is an elastic collision outside of the subatomic world. But in an elastic collision, momentum and kinetic energy are conserved. Because of that, there's enough information to find the 2 velocities, because it generates 2 equations. Now, we're not going to complete this problem, and here's why it's never on the exam. Let me show you what it looks like. The left side has not changed. 5 times 5 plus 0 equals 5v5 plus 10v10. This is the momentum equation. But there's also the kinetic energy equation now. We have more information. The system had 1/2 mv squared amount of kinetic energy. My watch just told me to stand up. You understand how terrible that is? I have not sat down. Mr. Lewandowski took away my sit-down moment. The moment I sit down between classes, so my watch knows that I'm not sitting. I've even been trying to gesticulate to tell the watch that. Nothing. It's very disappointing. 1/2 5 v5 squared plus 1/2 10 v10 squared. If it's an elastic collision, you generate more information. And because you generate more information, you have more that you can use to bring to bear on the problem. Now, you see, though, why we're not going to do this problem, right? It's a double quadratic. So there's a lot of math here. It's not terrible. You would have to solve one of these for velocity and plug it into the other, and then it's a single quadratic. It's not terrible, but it's a lot of labor. How many minutes do they want you spending on algebra that's tedious and can't be simplified any other way? Generally, no more than 1 to 2 minutes across the whole exam, which is why this is hardly ever on the exam. But I say hardly ever. It could come up. It's part of our curriculum. That's why I'm bringing it up. The most likely way they will do a problem like this is give you one of these velocities and ask you if it's an elastic collision. That's reasonable, because if they give you one of the velocities, you can easily find the other and then do this as a test to see if this is true. But remember, this is only true if they use that word. This is always true. We had work as our basis for discussion. Work equals force times displacement times the cosine. And, we derived everything from that. We didn't derive momentum, but momentum can be derived. I don't want to spend a lot of time on it because we have all of next semester and we have plenty of time. But the comparable term is impulse. Impulse is how you change something's momentum. So if work is how you change something's energy, impulse is how you change something's momentum. Work is more complicated because it can do so many things. It can change potential energy, it can change kinetic energy, stuff like that. Impulse can only be done by the net force. There's only one kind of impulse. There's not lots of kinds of work. Sorry, there's lots of kinds of work, but there's only one kind of impulse. Impulse is always the net force. Always. So impulse is the net force times time. Always. To change something's momentum requires an unbalanced force. It's the only way it happens. So we don't talk about impulse from each force. Never. We talk about impulse from the net force. And we will seldom ever calculate impulse. Seldom. I will do it in a couple homework questions. I've never seen it on the exam. I've never seen impulse on the exam. But it does equal the change in momentum. Now, I want you to think about the collision problem we just had. And this will be the last thing. And I'm talking about the any problem, where I have the two objects before and after, so 10 moving this way, v, and 5 moving this way, v, and this one being 5 and starts with 5. Right? The 5 kilogram block pushes on the 10 kilogram block. 5 kilogram block applied an impulse to the 10 kilogram block. It changed its velocity, right? That had to happen because the 10 kilogram block wasn't moving before and is moving now. By Newton's third law, the 10 kilogram block applied an impulse to the 5 kilogram block. In a collision, the total impulse is 0. Please just write that down. In a collision, the total impulse is 0. It has to be. The momentum doesn't change for the system.